Starting recording. So yeah, so since you guys are you want to know the mathematical background behind a lot of things, right? Even though we do not this is not really a math course, but it's definitely good to know. So I added one appendix to the lecture notes. I've uploaded in Moodle as well. Is the thing that I skipped, right, is I think in calculus 2 you learn how to write the gradient operator in Cartesian coordinates, but when we are solving the hydrogen atom and also for today angular momentum, we use spherical coordinates more. So the gradient operator in spherical coordinates takes a particular formula, right? But how do we transform from one into another? Actually, the conversion from Cartesian to spherical is basically just using the chain rule. But here, at least, if you have MATLAB or something if you can do matrix multiplication using a computer, then there's a very fast way to derive the Laplacian the gradient operator in spherical coordinates, right? Using the basis vectors in terms of the spherical coordinate as well. Okay, so then the Laplacian is just dot product with itself, and then do this. So if we have time at the end of today's class, I will talk a little bit more about this at the end of today's class. But for now, let us discuss the angular momentum, well, the general concepts of angular momentum in quantum mechanics. So yeah, so this one is like not tied to any particular system, but just the concept of angular momentum in general. We have spent some time understanding position and momentum already, right? And then we got the commutator. So, and then energy is depending on the system. We derive them by solving the time-independent Schrodinger equation to find the eigenstates. But how about the angular momentum? Okay, so why is this chapter going to be important? Is the following. It's going to be important in the future if you are interested in doing things like particle physics, you know, like the people working in the accelerators and things like that, because when you want to deal with particles, right, the important property of particle is going to be spin. So this is probably what we will discuss later in the next class. But there's two kinds of angular momentum. You also learn this in theoretical mechanics. An object, right? Let's say an object, even a planet, like a rotating body, it can carry two types of angular momentum. It can orbit around the center, right? Like the electron around the nucleus. This is what we call the orbital angular momentum. And then the second type is going to be, well, at the same time, it's going to have a spin, right? It's a rotation by itself around the axis. And that is the spin angular momentum. So today we'll just talk about this is more like related to the orbital angular momentum, and it will be the same angular momentum that is carried by the hydrogen atom, the M and L quantum numbers. Okay, so that is what we will try to do today. Okay, and because, you know, when Niels Bohr formulated the Bohr model of the atom, when he want to derive his results, he just like start with the assumption, okay, what if angular momentum is quantized, right? So in the Bohr model that you learned in modern physics last time, it starts as an assumption, and they only gave that assumption, and we know it is a good assumption only because we derive the result that can be checked with experiment. But at the time, at the level of the Bohr model, we don't really understand yet why should it be quantized, right? It's just a suddenly got assumption, suddenly you got the correct result. It doesn't feel very satisfying. But what we will do today is to derive this, explain this, and there's going to be a plot twist later, and it's actually connected to something that we already did before. Okay, so what we're going to do today is similar to what we did for the harmonic oscillator. We will use operators to do the solving the murder case and finding the energy eigenstates, momentum eigenstates, angular momentum. So let us start with some definitions. Okay, so as you have noticed by now, right, every time when you deal with quantum mechanics, the operator the important information is about the commutator. But first, let us define the definition of the angular momentum. It is something that we have already done since mechanics, right? Wait, am I recording? Always check. Always check. Yes. Momentum is, I hope everyone is familiar by now. In fact, those taking theoretical mechanics, you need to deal with this a lot, right? Especially rotating frames, Coriolis forces and things like that. Okay, so it's all interconnected, right? Everything is learning physics. So yeah, so this is the definition of the angular momentum. Last time when we did mechanics, or when you guys are learning, if you did mechanics without me but in high school or whatever, right? Normally at that level, angular momentum is just a number. You just care whether it's clockwise or anti-clockwise. But actually angular momentum depends on the axis. So the axis is a vector, and this tells us the information about the direction of your axis of rotation. So when you got the angular momentum, right, it is a vector. So let's draw a vector that is L. And why is the direction important? It just tells us that in which way the particle is rotating, right? So the axis is here. This is the plane of rotation. Then my particle is maybe something like this. So it's having the velocity v. Then using the right hand rule, it is this is the axis of rotation, and this will tell me the direction of the rotation. Okay, so this is when we did for, this is like classical mechanics. So this is our classical picture. Okay, so this is the important information that is carried here. So now we're going to do the quantum version. So how do we do the quantum version? Let's look at the these objects, these quantities here. This is r. So this r is just my position vector. Okay, so everything here is still classical. We will change this into quantum mechanics very soon, but we need to know what are the formula before we can change this. So the position vector is given by the standard form, right, as usual. And then this is the momentum. So this is a position, this is a momentum, right? In quantum mechanics, they will become operators. Px in the I direction, Py in the J direction, Pz in the K direction. So this is the linear momentum, right, in particular. And in doing this, will give us the angular momentum. So how do we compute this? I'm pretty sure you guys will do this in theoretical mechanics as well. If I take the full vector, I need to do the cross product, right? So do you remember how to do cross product? Okay, the first thing is you put ijk at the top, right? And then the first vector, so this is x, y, z. And then the other vector is px, py, pz. Right, so this is how you do the cross product. Cross product means you find the determinant of this thing. So how do you find determinant of 3 by 3 matrix? Firstly, we take the first entry at the top here. We follow one column, right? So we got the first entry, got the I over here. So there's something I, right? And then we find the determinant of the minor, okay? And then we use the alternating sign, plus, minus, plus. So the second term is minus the bracket J, and then the final term is plus the bracket K, right? So this is my way to calculate the determinant. It's a bit, for me, I find this easier to remember, right? And how do we find what is inside here? The inside here is the determinant of the minor. That's the language used in linear algebra. But basically what this means is we delete this column and we delete this row, and then we find the determinant inside. So the determinant inside is this minus this. So it's ypz minus zpy. Okay, and then in the middle here you delete this, the leftover is this minus this. So you got xpz minus zpy. And then lastly is these two things, these two rows and column delete, and then this minus this. So xpy minus ypx. Okay, so yeah, so then we got the these are my elements of my angular momentum. This is a vector, and this gives me the xyz components, right? So this is the x component of my angular momentum vector, and this one, be careful, there's a minus sign in front. This whole thing, whatever this is going to be the y component, and this thing is going to be the z component, right? Because angular momentum is a vector, so it has ijk components, right? And this is how you can write down the direction and the length and the magnitude and all those things. Okay, so at the moment, yes, everything here is as if this is a mechanics class again, right? But what we're going to do now is the quantum angular momentum operator. xpz. What do you mean? You mean the j direction, right? xpz, zpx. Oh, yeah. This is x, right? Correct. How about the rest? ypz, zpy. Oh no, the first one. zpy, yes. And then k is xpy, ypx. The rest, is that what you mean? Yeah, px, correct. Yeah, thanks. So good. That means you're following. Your brain is not melting yet. Okay, so now we got these components already, but the next thing that we want to do is to go to quantum mechanics. Yes, also yes, the negative sign, I haven't absorbed this yet. So let's write one more step. Because it depends on how you memorize this, right? The negative sign is because I remember this by calculating the determinant, but if I put in the minus sign, that this becomes negative xpz plus zpx, right, j, and then this becomes xpy minus ypx k. So this is the formula for angular momentum. Okay, now the next thing we're going to do is to go into quantum mechanics. That means observables become operators. Right, and in fact they become Hermitian operator in Hilbert space. So for position, as what we did last time, right, observable is a position. So in order to work in quantum mechanics, we change this to an operator x. The y coordinate is another observable, we change this to coordinate y and operator z, right? And then same thing for the p's, the momentums. So how do you change the momentum? Momentum px is h bar over I, derivative x, right? And then py, change this to h bar over I, derivative y, and then pz, change this to h bar over I, derivative z. Okay, so then now we let me quickly repeat everything that we have here, but now the only problem is these are now operators. So the quantum, in quantum mechanics, the angular momentum operator, so this whole thing should be giving us the position vector. So I will still write the vector notation, but the elements now are operators, right? This is kind of what we did in the previous chapter as well. And then the p is as well is also, p is just h bar over I, the I hat d dx, and yeah, no space. Let me put it down here. So then the momentum operator becomes p is h bar over I, and then in the I direction d dx, and then h bar over I in the j direction d dy, and then h bar over I in the k direction d dz. So here we notice that we can factorize out the h bar over I, everybody here, right? And then we got this, we recognize this as the gradient operator, the del operator, right? So this is d dz, right? So this is actually h bar over I, the nabla, the del. Okay, so this is my momentum operator. Position operator is like this. So now our expression for the angular momentum operator is written as the following. Is, well, we just change, so I still writing L here because there's not much, I'm running out of symbols to use. It's already in capital letter in mechanics, but this is now an operator, so it's now R cross P, right? So R cross P, and then this R is the same as before, but this P is actually H bar over I and then del. So these are constants, so we can take it out, and this is R cross and operator, okay? But in any case, we will still write this as Px, Py, Pz, right? So yeah, I should have written this, like Px, I didn't write this yet, right? So H bar over I d dx, Py is H bar over I d dy, and Pz is equals to H bar over I d dz, right? So the components of the angular momentum is through finding the determinant. So it's the same story that is happening here. The components are Lx is y pz, right? So y, and then p operator z minus z p operator y, right? And then the Ly is, there's a minus sign, this is a plus, so this is zpx minus xpz, right? And then Lz is xpy minus ypx. Okay, so we got the components now already. Okay, so everything clear so far? Yeah. So just now, right, the determinant. Del. The del operator. Yeah. So if you, so next time you can do, when you write a paper, you can invent a new operator called the HP operator, right? So now we got this. Important thing to notice is that when we are doing mechanics, right, these are numbers. Numbers, actually, we don't care who is in front, who is at the back. But now quantum mechanics, these are operators. So notice that all my P is at the back, all my Z is in the front. Why? Because we follow this, right? The position is in front, the P is at the back. So the order is now important in quantum mechanics. So now what we were going to, so we got angular momentum operators in x, y, and z components. So now let us check how they commute with each other. Okay, so the formula that will be useful later is, we're going to use this formula. So A times B commutator with C is ABC plus A, C, and then B at the back. Okay, so the order is very important, but let's check the commutators. Okay, so firstly, does Lx commute with Ly? Okay, so these are kind of like a new operator, but they are defined in terms of the existing ones. So let us find out whether they commute or not. Let's just put the whole thing inside. So what we have here is ypz minus zpy. This is going to be a bit boring, but I guess it was good to like go through it to get used to it as a practice. Commutator is a linear operation, so what we have here is ypz, zpy, commute with the first term. Okay, and then the second term got a minus. And let me know if I made any mistake. Commutator with xpz. And these two terms also has a minus, so I can split this up as well. So this is ypz commute with zpx minus zpy commute with zpx. Okay, so the first term is ypz commute with xpz, and then minus minus gets a plus, zpy commute with xpz. Okay, everyone follow so far? Okay, yeah. So I look forward to reading the discovery of a new operator. Okay. Yeah, by the way, you know, when physicists write paper, they name things in a weird names. They give weird names. So in cosmology, right, there's a theory of cosmology to explain dark energy, and they call it phantom dark energy. So the best story I heard, right, from the colleagues of the colleagues, why was it called phantom dark energy is because that paper was written in 1999, I think, and that was the year a Star Wars movie came out, Phantom Menace, and that is the only reason why it's called phantom dark energy. So until today, you Google the term phantom scalar field, there's a lot of research going on, and all this is because of a Star Wars movie came out in 1999. So yeah, if you call something HP Dell operator, it's not even the weirdest name that you can come up with. There are weirder ones out there. So let's do the operator. Let's apply this rule over here. But I think to save a bit of time, let us try to look at the structure of this, right? The commutator, right? So for commutators, as I explained last time, the commutator is xpx is equals to IH bar, right? And only along the same directions only, right? So the XP has commutator within their own directions. Right? So for example, X and then PY is going to be 0. If it's a commutator in different direction, it's going to be 0. And then for commutators, right? Also, yeah, position commutator with everything commute with itself, and then Z commute with Y also going to be 0. So different direction also commute. Momentums in different directions also commute. So anytime you see something in different directions, they will be 0. So from here, let us see, right? If I expand this term will have a commutator between momentum Z and Z direction. So this term is going to be important. But if I expand this term, right, everybody here, they commute with each other. So everybody here has commutator 0. So this term, let us save time, because if you work it out, you're going to get 0 everything. But it will waste a bit of time. So let us just say this lah. This will be 0. Okay, so same story happens here. Y, Z, X, and then PZ. So PZ commute with PZ. Everybody commutes. So this one also will be 0. So, and then this one will have, after I expand, I got some 0 and some non-zero terms. But let's find out, right? At least we can also use it as a practice for manipulating commutators. I'm going to use this formula. I'm going to use this formula over here. So this is A, B, and then C, right? So this is Y, PZ, ZP, X, okay, and then plus Y inside, and then PZ outside. Okay, so this is the first term, and then this term at the back is Z, PY, XPZ, and then plus Z, XPZ, and then PY. Okay, so the term, okay, so let's see now, who will be 0. So this one can be expanded. This will contain PZ commute with Z, so this term will have something there. But here is YZPX, so this term also will be 0. And then YXZ, everybody different, so this is going to be 0. Okay, so now let's expand this term. But this term is, the product is at the back. So if you are not so comfortable to how to expand this because you know the formula in the front, so if you're not very comfortable, then just change it. I flip it to the front with a minus sign. Right, so I'm going to do the same over here. I will flip this, so this becomes XPZ Z PY. Okay, now I can apply the formula which I'm more familiar with, because the product, this is ABC, so this is PXPZ, so this is going to be 0, and then this is ZPZ PX at the back, right? And then the same thing happens here. This is XPZ, and then plus XZ pz, and then remember to put the py at the back. Okay, so let's see if I made any mistake. This is very easy to make mistakes. Just check carefully. But firstly, this term is going to be 0, right? P, the two momentums commute. The two different positions also commute. So, and then this is zpx, so this is going to be ih bar, right, with the identity. So this is ih bar times px, so this is y ih bar px. And then what's happening here? This is zpx. So zpx is negative ih bar times the identity. So I got x negative ih bar, identity times py, you got this. So I think looks correct now. Both terms have ih bar, which I can factorize. And then this term becomes positive. So this becomes xpy, and then this becomes ypx. Okay. Now this one is what? xpy, ypx. This is exactly here. This is Lz. So after this long calculation, right, we recognize that if I commute Lx commute with Ly, it changes into Lz. So this is the commutator. So it's a bit of a long calculation, but it's at least worth doing once or twice so that we know where it came from, right? XY suddenly commutator becomes Z, and so on and so forth. Okay, so does anyone have any questions so far? Jiacheng operator, yeah, good. Yeah, if you work on something and people use it a lot, they will name it after you. Correct. Yes. This one. The reason is because these two have a similar structure. They are anti-symmetry, right? So there's a theory of math that is there's a common theory of math underneath everything. So there's a same thing. Some operator 0 and some not. Yeah, because so the reason is because well, it's like a postulate. You can treat it like a postulate, or we can just work it out like this, because well, firstly, like we can say that the x, y, and z are independent directions, right? So anything with different directions, they will commute, right? So so let us recall the commutators. So the basic one, right? The basic one that we have is the first one that we learn is because this thing is equal to ih bar, right? So this one we derive in chapter 3 by direct computation. Okay, so remember we use on the eigenstates, right? So on the eigenstates x, right? So if your x operate on x, you got this, right? So the position wave function of yeah. Anyway, let me write this. I mean, I shouldn't go through everything again, but you got this, right? So these are the position wave function of this is equivalent to ddx of this. So if you work everything out, right, you differentiate first and then you times x later, and then you times x first, you get later. So you got this, okay? And then this is for x and p, but x and p are just something that we call a certain axis. So of course, if we call the axis y instead, right, and then py, then there's no other reason. You have the same type of commutation relation, and then for the same reason, z also, pz also, we got the same commutation relation, right? And then also for now, let's just take by postulate. So for now, we take as postulate. The reason, right? I should try to think of a simpler reason, but the reason actually came from theoretical mechanics. So there is a theory in theoretical mechanics which you haven't learned yet, which have all this relation. But for now, let's take as the postulate commutators position across different directions commute. momentum also. So for example, x with commutator py, right? So because these are different directions, so this is for y direction, so they are going to be 0, right? So you do all for all the other things, like for example pz and then y also 0, and so on and so forth. So as long as they are different directions, in fact x with a different position also 0, right? So you can do it with all the other combinations, and same for the momentum. So px py also 0, and so on and so forth. Okay, so this is so the only non-zero commutators are these 3 pairs over here. Okay, so for now, yeah, let's take it as a formula. Okay, yeah, so like inner product, you know, with the 3 bases, and then what the commutator is like the commutator and cross product is what something called the Lie algebra structure of the thing, right? So there's a kind of theory going on behind there, but yeah, so you guys haven't learned yet, so let us not worry about that for now. Okay, so for now, let us take a postulate. These are the only 3 commutators. Okay, I should have started with this today's class, but next time, okay, yeah, next time I will remind everyone with this. Okay, so we have just done this computation, right? So this is just a brief reminder of formulas. But what we have just did was we have derived commutator Lx, and then this equals to this. So you can say that by similar methods, right, we can also calculate Ly, Lz. Okay, if you do instead Ly, Lz, you go through this whole thing over here, then you also get the something similar, but now it's Lx. And then if you do Lz, Lx is equal to IH bar Ly. Okay, so we got this. You can repeat the calculation again. Maybe you can try it, right? Since I already done xy to get z, maybe you go back and try by yourself yz. Can you get Lx or not? Right? And same story here, Lx and L this. But the reason why you don't really need to do this once you do this once, right, is you can do this by replacing your replacing the coordinates. Instead of xy, I replace this with yz, and then you just copy paste most of the calculation. You can get this. Okay, so yeah, so in essence we got the angular momentum operators all do not commute. Okay, so let me write this one more time as an emphasis or summarize. Right, Ly, Lz gives you IH bar. By the way, like Zero comment is very similar to cross product in another way also. Starting with 1, right, x, y, z, I can easily write down the other 2 by same thing like cross product. So what I do is I put the Lx at the back, right, and then I move this to the front. So this is Lx, Ly, right. Then to get the final one, I move the Ly to the back, and then these 2 I shift to the front. Okay, so the order is important. It must be in this order, because if I put Lz in front, it is the opposite order of the above, so it should be a negative of this. Okay, so it was the same story of how we did the cross product between the Cartesian basis vector, right? So the first thing is very easy to remember, ijk, but how do I get the other relations? So the I shift to the back, and then these 2 I move to the front, right? And then the last one I shift this again to the back, and then these 2 I move this to the front. So all these are called the cyclic permutation. Okay, so I got this in this order already. Then if I want to know k cross j, I need to flip it, then there's a negative sign. Okay, so yeah, so same story like this. And so on and so forth. Clear so far? Ah, yes, correct. H bar OI. Yeah, H bar is on top, right? H bar is upstairs. If you want to put I downstairs, then you put a negative sign. So yeah, so that's why XYZ is yeah, that's why I like XYZ order, right? Because just start with XYZ and then you don't need to memorize 3. You just remember this one thing and then you just reason out the others. But now why do we want to calculate the commutator? Well, the main reason is because well, since they are because the commutator is not 0, right? Commutator non-zero. So the consequence is there is an uncertainty principle. And then there is no common eigenstates. Of Lx, Ly, Lz simultaneously. Okay, and we have learned that these two are interrelated, okay, because these two are consequences of commutator being non-zero. Okay, so there's an uncertainty principle. That means if you measure the angular momentum is a vector, but let's say you do some kind of experiment to measure the components, whatever this is. You do the measurement, right, and then you get the uncertainties here, and then you do the measurement for y, you get the uncertainties here. And then by the uncertainty general formula, right, we have derived this in chapter 3 also. We got 1 over 2i. It is the expectation of the commutator Lx, Ly. Okay, so there is no uncertainty principle if I can get this to 0, but this commutator is non-zero, right? So this is the IH bar expectation value z. So that means the uncertainty principle is now depends on the I and I cancel, so I got H bar over 2, and then it is the expectation of Lz. Okay, so it depends, yeah, so as long as you got this thing over here, then you will have some kind of uncertainty principle. Okay, so there's an uncertainty principle and they do not share the same eigenstate, which is a problem actually, because when we want to find the properties of a system, right, we got operators, right, we got the observables, so we want to study what kind of things we can observe. We did this for energy, right? We got the Hamiltonian, so like a hydrogen atom, we find what are the energy levels allowed in this system. Harmonic oscillator as well, right? We got the Hamiltonian, we did all the tricks to find the eigenstates of the Hamiltonian, and we realized that they are quantized. So when we want to do the angular momentum, same story here. We want to find the eigenstates of angular momentum, and then we want to check whether the possible eigenstates are quantized or not. That means the eigenvalues can only take discrete steps. But then we already encountered a problem. We can't find the eigenstates. All these operators, they do not commute with each other. So eigenstates of Lx cannot be the same eigenstate of Ly, right? Or it cannot be the same eigenstate of Lz. Nobody commute with each other. So this seems to be a problem. And the way to avoid this problem is we consider something else, right? We make an observation. So even though these three do not commute, but what does commute is the total angular momentum. So everybody doesn't commute. Okay, so do you let me like emphasize again. Do you recognize why this is a problem? No common eigenstate means how do we even organize the issue? How do we even like express anything about this? If you know common eigenstate, then how can we find eigenvalues, right? We cannot even continue. So the answer or the solution, the trick is to consider L square instead. Okay, and the reason is because it commutes with L square does commute with its components. Okay, so let me explain what is L square. So L square is by definition L dot L, right? And L dot L is just Lx square plus Ly square plus Lz square. Remember, these are operators, so it just means that you operate x 2 times and plus operating y 2 times plus operating z 2 times. Okay, so let us check the commutator between L square and Lx. Okay, so yeah, let's work it out. This one is basically Lx square plus Ly square plus Lz square, and then this is, I want to find the commutator between Lx alone first. Let's see what happens. This is Lx square, commute with Lx, and then let me write it here. This is Lx square, commute with Lx, plus Ly square, commute with Ly, and then Lz square, commute with Lz. Hey, wait. Everyone is x. Okay. Everyone here is x, so no matter how you expand it, it's just the same operator, whether it's in the who is in the front, who is in the back, they are the same. So everyone here is 0, right? And then this one, I will use the formula again. This is Ly, Lx, plus Ly, Lx, and then Ly at the back. And then this one is Lz, so Lz, Lx, and then plus Lz, Lx, Lz. Okay, and then we put in the commutator relations that we have just found. X and y, right? So x and y is ILZ, I h bar Lz. This is y and x, so this is y and x. Is there something wrong? Hang on. Same thing, I h bar Lz, and then z with x is I h bar Ly, and then x with z is negative I h bar Ly. Okay, so if you work this out, this will give you Ly negative I h bar Lz. This is negative I h bar Lz Ly. Okay, and then this is I h bar can put in the front, Lz Ly, and then this is, hang on, zx, this should be plus, is it? Z with x, yeah, z with x is a plus I h bar Ly Lz. Okay, so this looks good because this is negative Ly Lz. These two are negative of each other, so you got 0. Okay, so they do commute. Okay, so now that we know that they commute, then this is Lx, but you can do the same calculation again. Similarly, L square commutes with Ly, also 0, and L square also commute with Lx, also 0. Okay, so now we got a set of a pair of commutators which do commute. Alright, so let me, before we continue, let us summarize what we have so far. So as we derived earlier, Lx, Ly is ILZ. Ly, right, cyclic permutation. So what I do is I shift the y x to the back, these two move to the front. And then cyclic again. So cyclic, I shift to the front. So this is how you use the cyclic permutation. And then the L square commutes with everybody. L square Lz equals to 0. Okay. So to describe the eigen, so now, right, we got at least, you know, all now that we know that everybody do not commute, then we don't need to worry about them. So because they do not commute, so what is happening here is, well, since all of them do not commute, they do not share the same eigenstate, what we are going to do is instead we focus on one of them, just one component. You can focus on any component you want, but the convention is people focus on the Lz, right, and then find its eigenstates. Okay, so find the eigenstates, and from the above reasoning, right, we realize that of course they do not commute, so will not be eigenstates of Lx and Ly. Okay, so they don't commute, so don't bother, right? We focus on one, they don't commute, fine, whatever, forget it, we can't. But because of this, but it will also be, will be eigenstates of L square. So at least we got something to, at least we got something else, right? So that means this is what we're going to do, right? So that is the eigenstates. Okay, so we denote the common eigenstates. What time is it? So so we're going to denote, right? So Lz and L square have the same eigenstate. Let's call them a ket. So let whatever this is, F, be the common eigenstates of L square and Lz and Lz. Okay, so that means, so we can write L square operating on F. So we want to find F, so we want to solve this equation. We don't know what the answer is yet, but if they are eigenstates, that means L square operating on this, it will give me some eigenvalue times this. Right, same story for Lz. If I operate on the same state, because they commute, so we know that we can use the same ket on this as well, it will still be an eigenvalue. Okay, so we don't know what these eigenvalues are yet. L square, so L square you treat as one operator. This is going to be eigenvalue. It could be one or it could be many, so we don't know, right? That is what we want to find. Okay, so that is our job next. Okay, so how do we find this? So we are for what time is it now? Eigenstate here means oh, got a question, is it? Correct. So if you use this notation in the lecture notes, oh, lecture notes, yeah, you're right, so it should be there. Eigenstate here means what? Yeah, it's just the eigenstate where if you add the momentum operator, then you get the excuse me. If you act on the momentum operator, suddenly something happened. I don't know why. Dust fell down or something. Eigenstate just means that it is a state, right? And it just satisfies this equation. Okay, so that that's all it means. Nothing special at the moment, but well, it's gonna mean something later. So I guess it's a bit of a spoiler, so we will keep it for now. Let us say we don't know yet, right? It will be like the ending of today. So it's a let's say it's a spoiler. So what we're going to do is let's try to solve this equation. And we are going to use the same trick that we did for harmonic oscillator. We are going to use the ladder operator technique. Okay, so we want to find both. Let's start with finding the eigenstate. So our job here is, what we want to do is we want to find the possible eigenvalues. So what are the number lambda and mu? So these are unknown variables, so we want to figure out what are the possible numbers. Okay, so we are going to do it by using the ladder operator method. Okay, so that is what we want to do now. Ladder operator method here is we define a creation operator and an annihilation operator, creation and annihilation operator, and then we define it in this way. So Lx plus ILy, right? They do not commute, but we will still use them to do something. Okay, so this and then this is just Lx minus ILy. So this is the Hermitian conjugate of this. Okay, so these are new operators again. So let's check what is the commutator. Let us see how they commute with Lz. So Lz commutator with L minus gives what? So it's Lz. L minus is defined to be this, right? Let's do plus. So this is actually very simple since we got all the commutation relations already, right? This is plus I Lz commute with Ly. So what do we have previously? Z with X is IHLY, and then Z with Y. So Z with Y is the reverse of this. So this is a negative IH bar Lx. So H bar can be factorized, right? I got ILY minus I times I just gets a positive one. H taken out already, so I got this. So this is just negative H Lx. Hang on a second. Plus ILY. So we come back to L plus again. So this is H bar L plus. So the commutator between Lz and L plus gives you back L minus. Okay, and then by the similar method, a similar calculation will give you yeah, this one is something you should probably try by yourself as a practice. For the minus, there's a minus sign. So usually in the shorthand notation, because plus plus minus minus, instead of writing double every time, you just compress it into one. Okay, so this is the commutation relation between our ladder operators with the, wow, so dark, ladder operators and the Z component vector. Okay, so this is how it works with Z. Then how about L square? Because L square commute, so the commutator is 0. So how does L square commutes with L plus minus? Well, L square is, L plus minus is defined to be Lx plus minus ILy commutator, right? But L square commutes with Lx plus minus I, L square commutes with Ly. So both of these are 0. So L square commutes, Lz commutator become L plus. So we can make use of this for the manipulation later. But for now, I think let us take a 10 minutes break. So this is page 4, this is page 5. Let's check, you see if you have any questions. So let's address any questions and then we break after that. Thanks. What do you mean? So you're talking about what we just did, right? Yes, because right now we have decided to focus on L square and Lz. Then now our ladder operator will now become so we will use the x and y for other things now, right? So we are kind of like separating z as special, and then x and y we will recombine them in terms of L plus L minus, and this will be our ladder operators. Ly plus minus Lz. Yes. Kind of, yeah. You mean if you use Lx here, that means here must be y and z, or vice versa. Okay. Yeah. Actually, yeah. Remember, right? At the end of the day, coordinate system x, y, z. These are just the names that we give, right? So maybe I call this x, or I call this x, or I call this x. So if we call some other thing x, then the other two must be x and y already, or y and z already. So that is that's all it means. Okay. Okay, tutorial 4, question 2a and b. Okay, yeah, good. Go ahead. Yeah, so let's take a break, and you can prepare for the tutorial, and then we continue the rest after this. Okay, so yeah, 10 minutes break. And let me stop the recording. We have found we have defined two kind of new operators, right? And this will behave in a similar way to the ladder operators that we did for the harmonic oscillator. But this one we are solving a different problem. But it turns out a similar technique can help us here as well. So the operator method is very powerful. Okay, so we define it this, and we define it like this. Okay, and then we check the commutator. And now that we know the commutator, we can now try to extract a few some information related to this. So the L plus and minus, they behave like the creation operators y. What did we mean by the ladder operator? It means that if I operate the ladder operator on it, it will create a new state, right? It doesn't keep the same state anymore, right? It's no longer the eigenstate. It's not an eigenstate. So when you operate on it, you get a new state. But this new state is still an eigenstate of your other operators, with the eigenvalue increase or decrease by a certain step. Okay, so to remind you, right, the F are the eigenstates of L square and Lz only. Okay, so this is eigenstate, and because Lz do not commute with x and y, right, and in fact they do not commute with L plus minus, the F is not an eigenstate of L plus minus, right? So let me at least write this now. So F are not eigenstates because of they do not commute, right? So that is our original problem. We cannot find the eigenstates of x and y. We gave up. Hence neither and not hence but neither L plus either. Okay, so it's not, so these are not eigenstates, but right, let us consider this. Okay, so I'm going to let this. Okay, so if I let L plus operate on F or L minus, right, these are not eigenstates, so this is not parallel to F anymore. So it's going to be some new step, a new state. Okay, so let us see what happens if I do this. Okay, so if I do this means what? So doing this means L squared operating on L plus and LF. Okay, and then because L squared commutes with L plus minus, I can change the order. F, right? So you can go from here to here because L plus minus L squared is equals to L squared L plus minus, right? You can commute, you can reverse the order, and then L squared plus this is lambda f. This was my eigenvalue, right? So that means what we got here is lambda is a number now. So the number I can shift it anywhere. So let me shift it to the front. I'll get L plus minus f, right? So this is back to G plus minus again. Okay, so notice that if I operate on this and I get a new state, but this new state is still another eigenstate of L squared, right? So that means L plus minus f is still also which is better, still an eigenstate of L square. And notice another thing here. Well, we expected to get a different state, but the eigenvalue is the same, right? With the same eigenvalue. As just f, right? So this is a new state which we call this G. But whatever this is, it is still an eigenstate with the same eigenvalue. So that tells me that this is the first hint that L square has multiple eigenstates, but they might have the same eigenvalue. Okay, so that is one thing. Then let's see what happens on when we play with Lz now. So now let's see how Lz works with G. So if I do Lz and if I operate on G plus minus, this is the same as Lz operating on L plus minus G plus minus. Okay, so how do I manipulate this? That's why we need a commutator, because I don't know what this does. Hang on, this is F. I don't know what this does, but I know what Lz does to this state. So I need to use the commutator, because what we have found that L plus minus is plus minus h bar. Was there an h bar? Yeah, h bar L plus minus, right? So this is Lz L plus minus minus L plus minus Lz equals to plus minus h bar L plus minus. So I want to change this to this. So this, we found that L plus minus Lz is equals to Lz Lz L plus minus is equals to L plus minus Lz and then plus minus h bar L plus minus. Okay, so now we got this now, right? So we just substitute the whole thing inside. So we got L plus minus Lz and then plus minus. You guys know what I mean when I do the plus minus, right? Hopefully you're used to it. It's rather than doing twice, doing a plus on one side, doing the minus on the other side. So this one saves time a little bit. So Lz L plus operates on F. So if I multiply this inside, I got this, right? So I got L plus minus F. Okay. Now this operates on this. This F was what we wanted as the eigenstate of Lz in the first place. So this gets mu, right? So this mu I can move it to the front. Then I got L plus minus F, and then plus minus h bar L plus minus F. So what was this? This was my state G, right? And then I can, in fact, I can factorize this. Sorry. So in fact, I can factorize the L plus minus here. And what we find here is mu plus minus h bar. And then this is L plus minus F. So this is Lzg plus minus is equals to G plus minus again. So Lz operating on G plus minus is equals to mu plus minus h bar G plus minus. Okay, so this is the effect of the ladder operator. So L plus, if I operate on this, I get a new state G, right? G plus. Then what is G plus? It turns out that if I operate Z on it, I still get G plus, but the eigenvalue is now mu plus h. Okay, so from here we recognize that L plus of this is also still an eigenstate of Lz, but eigenvalue mu plus it increased by h bar, right? We have also, we did this twice, right? We did both at the same time. If I do L minus, it is also still an eigenstate of Lz still again, but now the eigenvalue decrease by h bar. Okay, so this is interesting about what is this state. So L plus, so if I start with the original eigenstate, whatever this is, we don't even know this yet, right? But what I do know is, if we assume it's an eigenstate, then if I operate L plus minus on it, these are still eigenstates of L square and are still eigenstate of Lz. But for L square, you get the same eigenvalue, but for Lz, the eigenvalue increase or decrease depending on whether you do this or this. Okay, so notice that we have multiple eigenstates of Lz with different possible eigenvalues. You can go up and down, and this set are also eigenstates of L square common, but have the same eigenvalue. Okay, so that is kind of, we are still doing solving the murder case, right? We are detective. We are trying to identify what are the possible eigenvalues. We are gathering the clues, and these are the clues that we have so far until now. Okay, so this was page 6, right? Okay, now what else can we do? It turns out that the eigenvalues, right, the mu and lambda, it turns out that mu squared must be less than lambda, and I will explain why. Mu squared must always be less than equal to lambda. Okay, so let me tell you the reason. Okay, and the reason is this. So L square is what we have found in the first place to be L dot L, so it's L squared plus Ly squared plus Lz squared. Okay, so these are operators, but what if I find the expectation value? So if I close this with L squared with the eigenstate, whatever this is, right? So if I do the bra-ket into here, this is just bra f Lx square ket f, bra f Ly square ket f, and bra f Lz square ket f. Okay, so this is eigenstate, so this will become operating z Lz twice, will become mu square, right? Then this is eigenstate, so this becomes lambda, and then ff is just 1, so it's just lambda. So same thing here, this one ff, so this becomes mu square. Okay, so this, we don't know what this is, but what we do know is they must be positive, because this one, right, this is actually the norm of this operator f squared, right? So this term must be positive, and this term, same story, this is the norm of Ly operating on f squared, so it must be positive. Okay, but by the way, I'm skipping a few steps here. So is anyone confused why this is the norm of this? Do I need to explain? Do I have time? Okay, so if so just ask me whether I need to explain why this is positive, but for now, okay, so I got a positive number, right? So what we have here is mu lambda minus mu square, positive plus positive. So if I bring this over, then it must be a positive number, so therefore mu squared must be less than or equals to lambda. Still don't know f is what? Yeah, we don't know. That's the whole thing. We still don't know. We just know that it is some eigenstate that satisfy this equation. Yeah, we really don't know yet. We really don't know yet. It's just that whatever this is it is some ket that satisfy this equation, right? That's all we know so far, right? Yeah, we don't know. We really don't know. Okay, so don't worry about that. This is our detective investigation to catch our f, right? The ket f is the murderer, right? The criminal this is the crime, right? This thing happens, so this equation is satisfied, but we don't know what f does this. Okay, so yeah, so that means what we have so far is, let us summarize again. Some, to emphasize, to yeah, Zuri says don't know because we don't know eigenstate. All we do know is the murder. So this is what we say is the F is guilty of doing this and is also guilty of doing this. Okay, and the clues that we have so far is L plus operate on this is still an eigenstate of L with same lambda, and is still an eigenstate of Lz, but the eigenvalue now increase by h bar. Okay, and then the second clue that we just did was eigenvalues of Lz and a square must be smaller or equal to eigenvalue of L. Okay, so these are the eigenvalue of Lz. So that means I can operate this L square. If I operate again, then if I L plus square this, it will give me mu plus 2h bar, right? So if I operate this 3 times, this will give me mu plus 3h bar. So if I operate this many times, I will get a new state with eigenvalue that is increasing and increasing. So we might arrive at some problem here, because whatever this is, right, this equation must be true. The eigenvalue of mu square must be less than or equal to lambda. But if I keep on applying Lz too many times, will it violate this equation or not? Right? So this is our problem. If L plus is applied too many times, wait, am I recording? Test. Yeah, this part is recording here. Yeah, so this is why we keep saying, right, the operators is like essentially very magic. Norm of Lx squared. Lxf, the norm of Lxf. Yeah. Yeah, so about this, right, the step that I skipped was, let's look at the vector Lxf, right? And then the bra, if I take the conjugate, is f Lx dagger, but Lx are Hermitian. These are Hermitian operator is this. So the norm of Lxf is equals to this f, and this is f. So this is the norm square. So this f Lx square f, right? So this is how you get the norm, right? To remember to take the norm of a vector, right? So the norm of a vector alpha is the norm square is alpha alpha, right? And I replace alpha with LF. Okay, so just now what we were saying, yeah, if so this is the problem, right? If Lx applied too many times, then the eigenvalue of Lz square have a chance, or it will exceed lambda. Okay, so is it possible to violate this equation? This equation is actually nothing much, right? We are just using the basic concept of L square and the basic concept of norm. So nothing special is going on here. Then how can I come to a situation where it exceeded? So it actually doesn't. So this problem is avoided is because to avoid this contradiction, there must exceed a maximum state, which I will call F max, such that when the maximum is achieved, I got L plus F max, it will become 0, right? So if I operate enough times, I reach the maximum already, then if I try to increase this anymore, it will become 0. So this is one way to avoid the contradiction. So it is, remember this, when we did the harmonic oscillator, we did a similar proof, right? We went into a way more detail over there. It's a slightly different situation, but we argued that there's a 0 state of 0 eigenvalue, right? And then if you apply the decreasing operator even more, you get a 0, right? And that is because to avoid the non-integer eigenvalues. Okay, so there exists a maximum state. So the same problem also happens when I apply L negative too many times. L is applied too many times. So there also must exist some state that there is a minimum state, but if I want to decrease it anymore, you get a 0. Does that make sense? Do you agree? Yeah, so that is the interesting thing about angular momentum. So for the harmonic oscillator, the energy eigenstates are bounded from below, right? And then you can increase many times, but you cannot decrease too much because you hit a 0 and then you stop. But for angular momentum, it is bounded top and bottom. So if you increase too many times, it will stop. If you decrease too many times, it will stop. Because if not, it will violate this equation. And this equation is very fundamental. So we do not expect this to be violated. So that is the only possibility for statement 1 and 2 to be true at the same time. Right? So this is like kind of the mathematics thing that we're doing here. Right? This is also why like math is interesting for people who are interested in math. It's like solving the problem without directly solving the problem, right? Just by looking at the clues here and there, and then this. So far what do we have? Well, we have at least 2 new suspects, L max, F max and F minimum, right? So what we have is we got a eigenstate. One of the eigenstates is F max, such that the eigenvalue here, it will be the maximum F max, right? And I cannot increase this operator anymore. If I apply L plus again, it will exceed. So this is some maximum eigenvalue. And then according to this situation, the everybody for L squared, the whole time, the eigenvalue is still lambda the entire time. It's the same eigenvalue all the time. Okay, and then LZ F minimum, the same story happens here. There's going to be some mu minimum and then F max, right? And it is still the same eigenvalue throughout the entire time, but because in all our calculations, the eigenvalue of this did not change, right? And of course, for an so from what we have here is that we got the possible eigenstates of LZ and L square, right, which we label as F. Okay, we got F, let's start with F minimum, and then we got many, some arbitrary one is F, many, and then F minimum, F maximum over here. Okay, the brightness keep changing. So based on everything that we have so far, what we have learned, the minimum one, the eigenvalue, I will write in this table over here. So it's going to be mu minimum, and then the eigenvalue of LZ, this is mu maximum, right? So according to our reasoning so far, if I apply an operator L minus, right, the eigenvalue will decrease by 1 step, So if I apply this again, it will decrease again, and so on and so forth, right? And I can also go backwards. So if I want to go backwards, I apply the plus operator, right? Plus operator. So this thing, same story happens here. If I apply the, wait, this is plus, minus, right? Plus increase. Yeah, correct. So this is the maximum. So if I apply plus one more time, I get a 0, right? But if I go down, I need to do L minus. So if I go down L minus, I will get mu maximum minus H bar. If I go down again, I get mu maximum minus 2 H bar, right? So until some arbitrary state mu n. So I can go either direction by plus 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 until I hit the maximum and then it stops. But I can also go minus minus minus. I can get a minimum and then it will stop. Okay, so this is what we have over here. So this one is for some fixed lambda, right? So apparently all our calculation here is for the same lambda. So for some same lambda, the lambda can be big or small. So if the lambda is big, then the maximum can also be big, right? If lambda is smaller in size, then maximum and minimum must also be smaller in size. So it depends on the current value of lambda. Okay, so that is another information that we have so far. Okay, so this is why we got the ladder operator structure now in this angular momentum operators. Okay, so now to continue further, let us derive another formula, another identity. So let's see what happens if I do L plus times L minus, or L minus times L plus. So what do I get? Okay, so let's derive an identity. So I want to get a formula for L plus times L minus in the other way around. Okay, so that means if I do Lx plus ILy and then Lx minus ILy, right? So this is the upper sign. I become this, or if I do it the other way around, it's minus and then plus here. Okay, so let's expand this bracket. Remember, these are operators, so the order must be important. These two are in the front, these two are in the back. So Lx is the same. This one is okay, Lx square. And then times this term is minus plus I Lx Ly. So the scalar number, I can shift it anywhere I like. But for this case, this is plus minus I Ly Lx. And then plus minus, both are negative, right? No matter how you do it. But there's a I square, so it becomes positive again. So in other words, minus, let me write the details, IL square. So this becomes a plus, so Lx square plus Ly square. And then let us simplify this, Lx and Ly. So let me pull out minus plus I. So this becomes Lx Ly minus Ly Lx. Okay, now what is this? This is actually the commutator again, Lx Ly, which we have found earlier to be IH bar Lz. So this is the identity that we are looking for, Lx square plus Ly square, and then minus, so minus plus I, and then this whole thing is another I H bar Lz. Okay, so this becomes plus minus, right? So this set over here, and this part, let us express this in terms of L square minus Lz square. So these two have common eigenstates, so we've emphasized on this part as well. Okay, and then now I want to make this the subject of my equation. I bring everything to the left side. So I got L plus minus L minus plus. I bring this over, this becomes plus Lz square. I bring this over, this becomes minus plus H bar Lz. Okay, so now, right, now that I got this identity, I can now actually find out the values of lambda. And once I found the values of lambda, then I can get all the remaining values of mu already. Okay, so that is going to be another trick that we will solve. Okay, so the first thing that we want to do is I will take the upper signs. Start with the lower sign. And then I add this on F max. Okay. So why do we do this? So let's see, because we'll see what happens when we do this. So if I add this on L x max, right, this one is L, I take the lower sign, right? So the lower sign means I put L minus, L plus, I add this on F max, and then this one is plus Lz square, add this on the max, and then the lower sign plus H bar, and then add this on F max. Okay, so why do I do this? Because there's a L plus here, right? Remember we said that F is the maximum, so if I try to increase anymore, I will get a 0. So this term disappear. This term acts on F max 2 times, so this becomes mu max square, right? And then this term acts on this one, so this becomes mu max 1 time. Okay, so what we have here is this one is this one L square acting on F, so this gives me a lambda. So what we have found is the equation F max is equals to mu max square plus H bar mu max, and then all these are acting on F max. Okay, so in other words, I got the equation that is relating now lambda to the mu max already. So we actually have found the eigenvalues that given the lambda, I can identify what is the mu max. Okay, so this is what we got by taking the lower sign and add on F maximum. Then because up and down is kind of like the same, so the same calculation will happen if I take the upper sign and then I add this on the F minimum now, right? So I got L square F minimum, right? Now I take the upper sign, so I got L plus L minus, add on F min, and then plus Lz square, add on F minimum, and then take the upper sign, so it's minus Lz, add on F minimum. So if you do the same calculation, we find that the lambda itself can also be calculated as F. There's a minus here, so this is F minimum square minus H bar mu minimum. Okay, so from these two equations, let's call this 1 and 2, right? So if I compare 1 and 2, we conclude that mu maximum is the negative of mu minimum, right? So the number is the same, but they are negative to each other, so that when you reach the maximum of the mu squared for lambda, you get the same thing, right? So mu squared is this and that, and then we will see something familiar if we define the notation. So if I simplify the notation, I will let mu max be H bar times L. Okay, and therefore mu minimum is negative of mu max, so it's negative H bar times L, such that L is an integer. Okay, so if I do that now, let's see what happens. We conclude that my lambda is mu max squared, so mu max squared is H bar square L square, and then this is H bar square L, right? So what we have found is H bar square L plus 1. So you see something familiar? This is something that we encountered before, right? This is the spherical harmonics, right? So we got lambda is equal to H bar L plus 1. Okay, and now also we can also now label the eigenstates of the mu also. So for the any other mu, we let mu is equals to h bar times m, such that m is also an integer. Okay, so now we know, right? So now we can finally figure out the answer of lambda. So for some fixed L, we can conclude that lambda is equals to h bar L plus 1, right? And then the possible values of h bar m are, it depends on the m, right? So over here, the m can go from minus L, then minus L plus 1, minus L plus 2, dot dot dot, minus 2, minus 1, 0, 1, 2, dot dot dot, L minus 1, and then L. H bar 2, oh yeah, I forgot the h bar square. Yeah, you're right. Right, so for some fixed lambda, for some, the fixed L will determine the fixed lambda. And then L is an integer, because if I increase this, I can reach the L max. So the corresponding mu is equals to h bar times m. So this will give me mu minimum, right? Which is equals to h bar negative h bar L, which we have said earlier. And then the last one is, it will give me the mu max, which is equals to h bar L positive. Right? So finally, we have realized that the eigenstates of, actually we still haven't figured out what is eigenstate of f yet. So technically we still haven't really answered Zuri's question, but we do know the eigenvalues now. So the eigenvalues are these numbers. So these are the same eigenvalues that appear in the spherical harmonics. Remember, for spherical harmonics, right, the integer m must be less than or equal to L. So any number between negative L to positive L can be possible. And then this equation L plus 1 also appears, right, in the same way it appears in the we have seen this term in when we are solving the spherical harmonics. So yeah, at least we got it until that much. Okay, so it's 10:48. So Kaishan, have you figured out your tablet?
Yes, I think I have figured it out, and if not, I'll just use my laptop to present it.
Okay. Yeah, so you can go ahead if you want.
Okay, give me a moment. I use my tablet to join the meeting.
Okay.
Coming.